welcome everyone to today's Synergist webinar, Gas Detection in the 2020s, Gas Sensors and Big Data IoT. I'm Ed Rutkowski, Editor-in-Chief of the Synergist, the magazine of AIHA. I'd like to thank everyone for joining us today, and especially Industrial Scientific for sponsoring this webinar. Today's speaker, Dave Wagner, is the Director of Applications Engineering and Product Knowledge at Industrial Scientific. Since joining the company in 1986, Dave has been extensively involved with the development and application of portable gas monitoring instruments and the development of innovative solutions to complex gas monitoring problems. He serves on the NFPA 350 committee and has created a best practice guide for confined space entry. Dave earned his Bachelor of Science in Electrical Engineering from Penn State and a Master of Science degree in Management and Technology from Carlow University in Pittsburgh. Now I'm pleased to turn the presentation over to Dave.
Thanks, Ed. I appreciate it. First off, I want to thank you and the AIHA for hosting us today and allowing us to bring this event to you. As you said, we're going to talk about gas detection here in the 20s, sensors in particular, and then the role that gas detection is playing in the world of IoT. Just very quickly again, I'm Dave Wagner, Director of Application Engineering and Product Knowledge at Industrial Scientific. And for those of you that might not be as familiar with Industrial Scientific as some others, we work toward a vision, and that is that all the employees of Industrial Scientific are dedicating their careers to eliminating death on the job by the year 2050. Primarily what we do is gas detection, and certainly we can't get there ending death on the job through just gas detection. So that vision really drives what we do in gas detection and in other technologies and areas that we are looking at in terms of mergers and acquisitions and partners, and the way that we're running Industrial Scientific today. As I said, primarily we're known for gas detection, and that's our product, standard product, and what we have done for many years from our roots in underground mining to the numerous hundreds and thousands of applications we serve in industrial work sites, to places in emergency response, like you see here, the ground zero on 9/11, looking at gas detection on and below the earth. And then finally, as we see here, with the first SpaceX astronaut breaching the hatch into the International Space Station, and you can see there next to them in the hatch, gas detectors that we have been deploying on the International Space Station since it was first launched and first deployed many years ago now, taking and extending our mission to preserve human life above the earth as well. Today we're going to talk about a few things from a gas sensing technology standpoint. We're going to talk about the pros and cons of various sensing technologies that are used in real-time gas monitors today. And when I'm talking about real-time gas monitors, I'm talking about those devices that are carried by everyday workers in everyday applications around the world, whether it's being worn for personal protection, whether they're using it for confined space entry, whether they're using it for hot work permitting, regardless of the application. Those are the products, those are the technologies that I'm talking about today. And then we're going to talk about the role of gas detection and data in the industrial Internet of Things, and really bring gas detection into the 2020s and where we are today. Why is this so important? Well, just a couple of little numbers to throw at you that when you sit and think about them, really grab you and make you understand why we at Industrial Scientific and companies like us do what we do. According to a 28 United Nations report on toxic gases, Every 30 seconds, a worker dies from toxic gas exposure in their workplace. Every 30 seconds. Incredible. And we're not saying that every 30 seconds someone in a plant somewhere is dropping dead, but exposure to toxic gases is impacting our workers throughout the course and over the course of their lifetime. And every 30 seconds, someone is dying from a gas exposure they encountered in their workplace. The NRDC says that a pipeline carrying combustible products catches fire every 4 days and results in an explosion every 11 days, an injury every 5, and a fatality every 6 days. Numbers that really make you think and make you understand why our mission to make sure everybody goes home from work every night to their family is so important. And it's absolutely critical that we understand, that we talk about this and we understand the capabilities of the technologies used in these instruments so that we can make the right choices for technologies and the right choices for equipment and really understand how these products can be used to protect our workers and make them safer. It's amazing that every day I talk to people who are using these devices every day or recommending them to people, giving them to people every day to go out and use with the intent of protecting them or saving their life if need be, and they have very, very little understanding in reality of the way that device works and what it does. So it's really important that we talk about these things and we understand them, and hopefully I hope you learned something today that maybe you didn't know before. So we're going to dive into the gas sensing technologies, and we're going to start with combustible gas sensing. When we look at those pipeline numbers, you know, any gas accident is tragic. There's no question about it. But accidents from combustible gases, fires, explosions, become catastrophic very quickly. And so it's really important that we understand how to detect combustible gases. And the first technology we're going to talk about is the catalytic bead technology. We'd be really missing out if we didn't, because still today it's the gold standard in detecting combustible gases. It's the technology that came following the flame safety lamp and detecting gases with just simply an open flame. And catalytic bead came into place and took over. And one of the reasons it did is because it is a very simple technology that's capable of detecting any combustible gas or vapor, as simple as that. Now, a lot of people might dispute that and say, well, you can't detect vapors off of hydrocarbon liquids with a combustible gas sensor. You can't detect with a catalytic bead sensor. You can't detect heavier hydrocarbon vapors with a catalytic bead sensor. And I would tell you that that's not true at all. You can detect any combustible gas or vapor with this technology. The limitations come from basically the mechanics of the sensor and the way it's constructed, and filters that might be installed secondarily on the sensor. But the technology, and all sensors are different, but the technology itself is capable of detecting any vapor that's combustible. The sensors have a very, very linear output, and they're very easy to implement. If you have a catalytic bead sensor, a battery, and a voltmeter, you've got a high school science project and just made a combustible gas detector. Very, very simple to implement. But they're certainly not without their shortfalls. Definitely some fundamental problems that come with the catalytic bead sensor. First and foremost, I said it can detect anything combustible, which it can. It can't speciate anything. It will see it. It will know it's there, has no idea what it is, which is often very important. One of the biggest downfalls of the catalytic bead technology is it requires oxygen for accurate combustible detection. It's not a limit of the technology per se, it's a limit of physics. And you need, stoichiometrically speaking, you need 10% oxygen to be able to detect and burn and catalyze 5% methane. It's as simple as that. The sensors require oxygen, and below a certain oxygen limit, which is different for every sensor, it's certainly limited. All catalytic beads are susceptible to poisons, primarily silicones and sulfurs, a few other things in there as well. And the level of susceptibility is based on, again, the construction of the sensor, the construction of its catalyst, and it is very proprietary in nature, but they're all susceptible to poisons. And along with that, they can be influenced by changes in humidity pretty dramatically. I'll explain that a little bit later when we're talking about another technology. And these sensors have a very high power budget as well. If you're going to run a catalytic bead sensor and you're going to run a good catalytic bead sensor and make it very reliable, it's going to take some power. And that becomes a difficult obstacle when you're trying to make a portable instrument that someone's going to carry for a while. How do we overcome those shortcomings? Well, you would think there's got to be a better mousetrap, and that technology's been around forever, and you think there's got to be something better out there, and a lot of people think there is. And that technology is infrared, non-dispersive infrared, or what today we're calling ULPIR, or ultra low power infrared, as the case may be. And a lot of people have seen this as the cure-all for combustible gas sensing. And there are some good reasons why. There's no O2 requirement. You can detect combustible gases in a completely inert atmosphere. Certainly applications for that, applications where the catalytic bead technology struggles. The infrared technology thrives there. There's no poisoning. You can't poison an infrared sensor, particularly in the case of the ultra-low power sensors. There is a very, very low power consumption, so you're not eating batteries, not having to charge instruments every night, and you certainly get a long life out of these sensors, as there's no part of the sensor in particular, particularly LED-based infrared sensors, that has a consumable component. So the sensor's very long life. But as I said, they're not the cure-all that everyone thinks they are, and there's certainly some pitfalls to using infrared sensors. The first is they don't detect hydrogen. Often misunderstood in many of the applications you run into. The first question, are you going to have any possibility of encountering hydrogen? And if you do, then the infrared sensor has to be out. We can't detect acetylene or other compounds where the infrared absorption isn't as strong, or it doesn't fall within the absorption band of the sensor. Infrared sensors have poor linearity in general. The technology is not inherently linear, and so it has to be compensated for to make it linear. And there's generally a poor correlation between gases, where the outputs of the catalytic bead sensor are linear, and it's very easy to correlate one gas to another, response to another based on what a sensor's calibrated to. The same doesn't apply to the infrared sensors. Very, very poor correlation, and a sensor and a gas that is other than what the sensor's characterized to and calibrated to can cause you some problems. If we go back a little bit in time, certainly before infrared and when the catalytic bead technology was becoming that standard, people were using a lot of MOS sensors and thermal conductivity sensors to detect combustible gases. And they brought some of the benefits of the catalytic bead in terms of a broad spectrum detection. They had wider measuring ranges than the catalytic bead sensors, allowing you to see from VOC levels of a lot of hydrocarbon gases up to 100% volume of gas in many cases at a very low cost. And the reason I talk about this technology today, even though it's not really used that often anymore in the types of instruments I'm talking about, there are people working with thermal conductivity sensors or MOS sensors today in different ways than we've seen traditionally, setting them up in arrays and looking at the response to them to find different characteristics by manipulating the input to them a little bit, and then characterize them to be able to speciate particular gases, speciate and quantify different combustible gases, which is a real benefit that it brings in terms of technology. But again, there are downfalls. As much as a thermal conductivity sensor is a broad spectrum type of detection, and the flip side of that they can detect anything is a problem as well. They'll detect anything that has a thermal conductivity different than air, and that goes beyond combustible gases. It goes beyond what we consider typical TICs or toxic industrial chemicals. They'll essentially detect anything. There are some pretty famous stories out there about people getting onto buses and natural gas powered buses and things that had been equipped with sensors, thermal conductivity based sensors, and based on all the people getting onto the bus and the perfumes and the hairsprays and everything else, the sensor shut the bus down and locked the people on the bus in the middle of a 100-degree day in Houston. They can detect anything, and sometimes that's a problem. They're very, very susceptible to changes in relative humidity because, again, they're detecting anything that has a thermal conductivity different than air. And when I say different than air, different than dry air or the ambient air that the baseline of the sensor is established in. And when you introduce moisture into the atmosphere, you change the thermal conductivity, the response of the sensor changes, and the sensor is susceptible to that. That harkens back to what I was mentioning about the catalytic bead sensor as well, being susceptible to relative humidity. Because if the two elements of the sensor aren't perfectly matched in resistance, and you introduce a lot of moisture, a lot of relative humidity, or you dry the atmosphere out significantly, if the two elements aren't perfectly matched in resistance, they change independently with respect to the thermal conductivity, and they change differently, and they produce an output that, as an end user, you see translated as drift, and the sensor drifting all over the place. So relative humidity is a definite problem, and the thermal conductivity sensors still can be susceptible to poisoning, not completely immune to that. One of the technologies that I have a lot of hope for that is starting to come into play today are carbon nanotube-based sensors, not just for combustible gas sensing, but in general gas sensing as well. There's a lot of hope for carbon nanotube-based sensors from the fact that they provide an opportunity to have, based on their size, There's very, very small surface area. The materials, very low power combustible gas detection. As I said, when we're talking about catalytic bead sensors, power consumption is their Achilles heel. Carbon nanotube sensors have the potential to solve that problem. They have the potential to speciate gases if they're set up properly, and because they're very small, it's easy to build an array of a number of sensors, maybe even hundreds of sensors that can all be characterized differently and really allow you to be able to speciate a gas. Typically, no oxygen, no poisoning, but again, while there's a lot of research being introduced in carbon nanotube-based sensors, there's no sensor that has really been commercially successful on the market yet to a large degree, and these sensors have no proven field history. So while the technology is very promising, and I think the future of combustible gas detection lies in this technology, it's certainly not there yet. So that's where we're at combustible technology-wise. Let's turn our attention over and start talking a little bit about toxic gas sensors. The standard for toxic gas sensing today is still the electrochemical sensor. These sensors bring the highest level of specificity to toxic gas detection. They're not completely specific, but when we're talking about combustible gas sensors that have very, very broad-based detection and will detect anything combustible or almost anything in some cases, electrochemical sensors for toxic gas have a really, really high level of specificity. They bring relatively long life. I have seen and just saw the other day a H2S sensor that was alive and working in an instrument that we have not made since the mid-90s. So these sensors can have a really, really long life at sometimes, and they're relatively low to moderate cost. So it's pretty easy to make a toxic gas sensor for some gases given the right components. But again, they are not without their downfalls. Electrochemical sensors are either based on an oxygen reaction or an oxidizing reaction or a reduction reaction, and as such, the output is positive or negative depending on the reaction, and because of that, cross interferences can be positive or negative as well. And the biggest thing that I see in misunderstanding of electrochemical sensors and response from electrochemical sensors is that you have negative cross interferences that people don't understand. In many cases, they don't know that they exist. They're troublesome because they're troublesome. Many instrument manufacturers block the negative signals, which makes them all that more troublesome. Because sometimes the only way you know a particular gas may be present is if you understand that negative value you get from the sensor. One of the biggest limitations of electrochemical sensors is they're not available for all gases. There's still today many gases we get called about every day, someone looking for a sensor for, and there's just not one available. Another problem is that, again, technology-wise, the sensors rely on old technology. You can only stretch chemical reaction so far, and organizations like the ACGIH, NIOSH, they're reducing recommended limits on exposures all the time, and many electrochemical sensors just can't get there. They can't get down to the levels that are needed for high quality high quality assessment of toxic gases in some cases today. And on top of that, sensors are typically pretty averse to a lot of the bad environmental conditions that they're used in. A lot of toxic gas detection, in some cases, particular toxic levels of hydrocarbons, has gone to photoionization detection, or the PID. And the benefit of a PID is that you get very low level detection of VOCs and other gases, in some cases down to ppb levels, over a very broad range of detection. And one advantage that the PID has is that there is a very clear line of what you can and cannot detect with the PID based on the lamp voltage. If your ionization energy is above 10.6 or ionization potential is above 10.6, you're not going to detect that gas with a 10.6 lamp. As simple as that. If you want to detect methanol with the PID, you can do it. You're not going to do it with a 10.6 lamp. You're going to do it with an 11.7, but that capability is out there, and you know where the line is at. And fortunately, there are multiple lamp voltages available to be used within PIDs. Problems, though, like every technology, there's an Achilles heel. One of them with the PID is that it can't speciate. Very widely misunderstood because of the use of correction factors and response factors. That people using PIDs tend to believe that, well, you just dial up the response factor for MEK, and that means that the PID is detecting MEK. Not true. You can't, very, very difficult, and generally you can't stop it from detecting anything and everything that is sitting underneath the ionization energy of the lamp. But users misunderstand and believe because of the correction factors that you can. One thing that's widely misunderstood about PIDs is if they're not used very often, if they're used sporadically, they have a long warm-up time. The lamp has to warm up, the lamp has to burn in, and if you don't understand that and you don't know it and you don't use it all the time, you spend half your morning when you fire up that PID and need to get a reading very quickly, chasing the baseline on the lamp while it warms up. Some models of PID are very sensitive to relative humidity. Some PID models have cured this and it goes away and is not a factor anymore, but many still are very sensitive to humidity and something to be aware of. And then as I said, there are multiple lamps voltages available, and some things that you really need, like methanol, that 11.7 EV lamp to be able to detect. 11.7 lamps are very expensive and they have a very short life. So if it's not something you're doing on a regular basis and you need an 11.7 lamp to do it, you're probably better off going to some type of tube technology or some other technology that's not typically used in a standard gas monitor and doing it that way, because you'll spend a fortune in trying to work through 11.7 lamps. So that's really everything that I think. Oh, nope, we left out one major category here that we want to talk about, and we can't move on without talking about, and that's oxygen. What's going on with oxygen sensing? Well, we have the galvanic fuel cell, which has been the standard in oxygen detection for years. One of the reasons it's very easy to implement. This is even an easier science project than the catalytic bead sensor, because you don't need a battery. If you have a resistor and a voltmeter, you've got an oxygen detector, or at least an altimeter, depending on what type of oxygen sensor it is. So it's very easy to implement. There's virtually no power consumption. But on the downside, the galvanic fuel cells are lead-based, and because they're lead-based, they have a very finite lifetime. Once the lead in the sensor is consumed and converted to lead acetate, the sensor's dead. As I said, that lifetime is very finite based on the output of the sensor, and it is and the end comes very quickly. They will die catastrophically very quickly and with very, very little warning. So not perfect, but there's a new oxygen sensor today, and that's the oxygen pump. And the oxygen pump works more like a standard electrochemical sensor just used to detect oxygen. They have a very long life and can be measured in terms of numbers of years like many of the electrochemical sensors. And the best news is they're environmentally friendly for the most part. They're lead-free. They don't rely on the lead. So you can use them without having to work through exemptions in things like the ROSE directive and RoHS and areas like that. They're lead-free, but oxygen pumps these oxygen sensors operate on a bias voltage, and because of that, they can be troublesome. If they're left off bias for a while, it takes them a long time to warm up and a long time to stabilize. So if you don't keep your instrument charged all the time, then you run into some difficulties with them. That takes us through the technology and gets us into where we are in the 2020s and the role that gas detection is playing in the Internet of Things and in terms of big data. And it really comes down to the focus of gas detection changing from self-reporting and data logging to connectivity and live monitoring and real-time data. And what I mean by that is that we have changed from the days where we hand someone a gas detector and we rely on them maybe or maybe not telling us at the end of the day that the gas detector went into alarm and they were exposed to 189 ppm of H2S, or looking on the data logging files that are reviewed after an incident and usually only reviewed after an incident, to being connected to that monitor all the time and getting data from it in real time, right now, live, and being focused on things like team-based safety, where monitors can communicate with each other and workers can know what their teammates or people working around them are exposed to based on their monitor. And applications like plant-wide monitoring, where we can see all the gas detectors on all of our employees at one time and see what they're being exposed to right now in real time and see where they're at. That takes us to lone worker safety, where we go beyond gas detection and we can see what's happening with those workers that might be out alone on job sites, where they work independently, where they might not have a partner, where no one is watching them, but they still encounter problems that may take away from their safety, right down to applications like e-permitting, where we can use the gas detector and we can get readings from it in real time to populate things like hot work permits and confined space permits and make those processes all more efficient and more productive. When we look at work sites where these types of gas monitors are used, they look a lot like this. They're big areas and big job sites or workplaces that have a lot of variability to them and a lot of different applications, whether it's and today, without being connected, as someone responsible for safety or that loss or the environment in a plant, you're sitting over here in one of these buildings with no visibility to what's going on outside of that office or outside of those windows. And today, through connectivity and being connected through the gas detectors, we get better insights into what's happening into those facilities. We can look at fence line monitoring in real time. We can do heat mapping of hazards. We can look out into the tank farm and see what's happening in the tank farm gas-wise in real time. We can do muster point management, know where people are at. We can remotely monitor our confined space entries, automate the permitting process for them, and see what's happening in multiple confined spaces and work to monitor and serve as attendants on many confined space applications and scenarios all at one time by being connected. So tremendous advantages that connected safety and connected gas detection brings to us. Some of the benefits are faster emergency response. We can see what's happening with an incident in real time, not have to wait till someone calls on the radio, if they do, or someone comes back into a plant and says, hey, my gas detector went into alarm today. We can see that in real time, and it makes emergency response much faster. We get data. We get more data. We get it in real time. It helps us enhance worker health. It helps us enhance wellness. It helps us enhance productivity because we can make their jobs more efficient based on seeing what hazards they're exposed to and when those hazards are occurring and on what jobs those hazards are occurring. And all that helps us diagnose and predict and prevent future incidents. If we know the conditions that occur or occurring in a particular area routinely or on a particular job routinely, and we don't take steps to move into the future and correct those conditions, we are really missing out. And connected gas detection and connected safety has the ability to do that for us, along with, giving us a real ability to define and identify areas where we have the most risk. But again, just like our technologies, connected gas detection, connected safety, it's not without its challenges. It's not without its pitfalls. And the first one is it relies on connectivity and having reliable connectivity. And without connectivity, we don't have anything, which is why the safety world has been so slow to talk about wireless gas detection and wireless safety in the first place, is because it has to be reliable. And beyond that, we get into the issues so prevalent today of data privacy and data security. And beyond that, what do we do with the data itself? How do we store it? How do we store it? How do we store it securely? How is it retained? How is it backed up? What do we do with that data? Who owns the data? Who has access to the data? All of those things come up as challenges of IoT and connected safety and live monitoring with respect to any device, just not gas detection. But I can tell you, when you look at the end of the road, the benefits certainly outweigh the risks and make you drive to overcome those challenges. And I'll just leave you today with this picture and this thought. None of those workers in that picture expected to go to work that day and have to run from that scenario to protect themselves and save their lives. We are here today to prevent that. And we believe that connected safety and being able to monitor those workers, gain as much information as we can from them, provide them with as much information as we can about their surroundings, what they're being exposed to, what the environment they're working in is, will help prevent the scenario that you see depicted here. So with that, I will thank you for your time and turn things back to Ed.
Okay, thanks, Dave. It looks like we've got about 15, 20 minutes for questions. Just a reminder for our audience, if you'd like to ask a question, please type it into the chat window on the right side of your screen. And our first question today comes from Eugene, and he asks, do you have any thoughts on an LEL NPS sensor that adjusts to the type of gas to read a corrected LEL?
Yeah, I have a lot of thoughts on it. I know the sensor that you were talking about, and that sensor has, believe me, a lot of promise. It really does. And since you asked the question, I'll answer the question. If I were making a gas detector today that was strictly going to be used as a personal monitor, that I was going to hang on myself and walk around my job site with and expect that sensor to operate and perform and work accurately, I absolutely would endorse it and would use it. But the problem is that, like I said, technologies generally have one Achilles heel, and the Achilles heel of that one right now seems to be that it doesn't like depleted oxygen concentrations at all, and so it's virtually impossible to use it in an application like a confined space entry, because it's very inaccurate in lower oxygen concentrations.
Okay, thanks, Dave. Next question is from Jennifer, and she asks, please share your thoughts on disposable gas detectors without calibration versus calibratable ones.
Wow, that's a deep question. So disposable gas detectors. Disposable gas detectors certainly have their place, but it's difficult to say that a gas detector doesn't need to be calibrated. Sensors, if you look at any of the gas detection sensor manufacturers, the raw sensor manufacturers, they're going to tell you and show you and specify that the sensor has a drift component over time. And the only way that you can compensate for that drift component accurately is to calibrate it. And to calibrate it, you need gas to do it. Now, if you're not concerned about the overall accuracy, that's fine. But when we get into conversations often about, this gas detector, we set the limits at 2 ppm or 10 ppm, and if it's reading 11 ppm and alarming, and we don't think it should be, then we're complaining about that. It's not reliable. Well, it can't be reliable at those levels without being calibrated. That's as simple as that. If you're going to be in that area, then you have to have a calibratable monitor. More important than calibration, though, I would say is bump testing. If you're not going to calibrate it, you certainly need to be bump testing it, because the only way you know it'll detect gas is to test it with gas, regardless of what anybody says. I can pick up any instrument and I can tell you whether the sensor is present any number of ways electronically. But the only way I can tell you that it's going to detect gas is to test it with gas. The only way I can tell you that gas is going to actually get into the sensor is to test it with gas. There is no other way. And when those capabilities start to be reduced, calibration is the only way of compensating for them. So I think that's about the best answer I can give on my position on that.
Okay, thanks, Dave. Next question is a two-part question, and the first part is, what are the most detrimental interference gases for H2S detectors?
The most detrimental interference gases for H2S detectors. Probably the most detrimental would be the most detrimental. First off, I would say this, that cross-interfering gases generally don't hurt the sensor. They don't damage the sensor. They don't reduce the life of the sensor. It's just another gas the sensor is reacting to. So detrimental from that standpoint, I would say there's little to nothing. When you get that, when cross-interference has become really detrimental, it's when they're misunderstood. And as I alluded to, those negative cross-interferences, things that tend to maybe produce a negative response on a sensor like an H2S sensor, like NO2, or something like that, ozone maybe, where the reaction on the sensor might be negative and actually block, because it's negative, it blocks the response to the target gas. So, for example, if you have a gas that has a negative cross interference on an H2S sensor, and that cross interference measured is relative to negative, just throwing out a number, negative 5 ppm H2S, that means it takes 5 ppm of H2S to get back to 0. And if your alarm is set at 10, it takes 15 ppm of H2S to get to a point where you put that instrument with that sensor into alarm. So it's those negative cross-interfering gases that are the most detrimental if they're not understood.
Okay, thanks, Dave. And the second part of that question is, are there any other factors that may lead to false alarms?
Well, sometimes you'll have false alarms on some electrochemical sensors due to relative humidity or transient responses to relative humidity. But I really have a hard time with false alarms on a gas sensor, an electrochemical sensor in particular. And the reason is this. A gas detector, an electrical chemical sensor that's producing a response, particularly a large response, or a response that is causing it to go above an alarm threshold, is detecting something. It doesn't happen for no reason. That sensor is detecting something. The question is what it is, and what it is may be just as harmful or more harmful than what it's supposed to be detecting. So it's hard for me to classify that as a false alarm. It might not be H2S, it might not be CO, it might not be SO2 or NO2 or whatever the case is supposed to be, but it is something. And identifying and understanding and knowing what that something is critical. And it's better to know it than just be frustrated. You know, it's better to know it and ease your frustration than have something bad happen because the sensor wasn't able to identify that it was seeing something in the first place. If you follow my line of thinking.
Okay, the next question is from James, and he says, I've been told that gas monitors' lives are dramatically reduced when they're not used regularly. Is this true?
Well, that depends on really what sensor you're talking about. I would say no, that's not true. There are some sensors, like the oxygen sensors, in the galvanic sensors that are being used and consumed, whether the instrument's in use or not. That's just a fact. Unless you want to store the instrument in pure nitrogen, it's going to consume that sensor. And there are other situations where you're looking at very, highly reactive gases, maybe like HCl or HF or something like that, where the surfaces of the instrument or the gas delivery system to the instrument will absorb those gases quite readily and prevent them from ever getting to the sensors. And if they're not used readily and exposed to those routinely and exposed to those gases routinely, it takes a while for the surfaces to all reach equilibrium so it works better. And those things may be interpreted or display themselves as a shortened life on the gas detector. But in general, I would say that's not the case. But at the same time, if we have them, we should be using them.
Okay. Thanks, Dave. The next question is from Derek, and he asks, is there something greater than an 11.7 lamp?
Nothing that I'm aware of. I'm not a huge expert in the PID technology, and we don't deal even with 11.7 lamps because of the pitfalls that I mentioned. So as far as I know, 11.7 is where you go, is as high as you go.
Okay. Next question is from Michael, and he asks, are you investigating the use of metal organic frameworks, or MOFs, in your detection systems, and if not, why not?
Well, I can say we aren't currently. And why not? It's just not something that is really on our radar at this point or anyone has introduced us to.
Okay, thank you. And the next question is from Brent. He asks, he says, I have trouble working with other OHS and IH people using correction factors for PIDs with an unknown mixture of chemicals. Do you have any advice in educating them?
Oh, boy. Yeah, so it's really, really difficult and this is where I said that the correction factors really get misunderstood and misunderstood how they're applied. And that's on a particular gas, and it even gets worse when it comes to mixtures. And I don't have a lot of good advice on that, other than make sure you know what the mixture is. If you know what the mixture is and you know the percentages of each of the components, then you can calculate what the correction factor is pretty easily. But if you don't know the mixture, you don't know the makeup and the percentages, there's not much you can do.
Okay, and the next question is from Eugene, and he's asking about bump test recommendations. He says, some people go a week or a month, then do 3-month calibrations. I have seen recommendations of daily bump testing and monthly calibrations. Or do you have any changes to that?
Yeah, well, again, like I said, this question puts me on my soapbox, is that the only way you know that a gas detector sees gas is to test it with gas. And I always tell people this: if I had my own, this is not a technology question. If I had my own personal gas monitor that I myself was responsible for, no one ever touched it but me, I put it in my drawer at night and knew that it was there safely, no one was messing with it, no one dropped it, nothing happened to it, I am perfectly comfortable taking that gas detector out of the drawer a month from now, 3 months from now, 6 months from now, turning it on and being very secure in the fact that it'll save my life. But that is not the way gas detectors are typically used today. And the fact is, when someone goes in and they pick that gas detector up off of that charger, or take it out of the back of the truck, or wherever it's at, they have no idea what happened to it when the person used it last. What it was exposed to, whether it was dropped, was it fished out of a bath of oil? Usually you can tell that. But you get my point. You don't know what had happened to it. And if you would want to bet your life on using it without bump testing it and knowing it worked, then that's your decision, not a decision that I want to make for myself and wouldn't recommend for anyone else. So again, calibrating it every month even, or every 3 months, or every 6 months, certainly doesn't, and so you calibrate every 6 months and it fails the calibration. Or you bump test it, I'm just going to bump test it once a month, and it fails the bump test. The problem is you don't know what day of the month before that it failed on. Did it fail on day 1 or did it fail on day 29? You have no idea, and that's why you have to bump test that. At Industrial Scientific, we've countered that to some degree with our Tango single gas instrument that has dual sense technology that is giving you 2 sensors, putting 2 sensors in play at one time, all the time, and basing a reading off the output of both of those sensors at the same time. And the logic behind that is that having both of those sensors failing catastrophically at the same time is highly unlikely. And to the point that our data says you would be 85 times safer carrying that instrument without bump testing than you would if you were carrying a standard single sensor instrument and bump tested it that day.
Okay, thanks, Dave. And I think this is going to be our last question today. We're close to the top of the hour. Warren asks, is there an app available that would recommend the best detection method for a specific gas?
Ah, wow, that's a fantastic idea. I don't know of one, but it's something to definitely think about and potentially start working on. And hopefully nobody in the audience beats me to that. But if you do, fantastic.
All right, well, unfortunately, that's all the time we have for today, Dave. My thanks to Dave Wagner for his presentation, to Industrial Scientific for sponsoring today's webinar, and to all of our participants. I hope you're able to join us next week, November 17th, for our next product demo webinar, when OHD will demonstrate their QuantiFit respirator fit test instrument and QuantiCheck quantitative user seal check device. You can register at aiha.webvent.tv, and have a good rest of your day.
All right. Thank you, everyone. This actually concludes today's webcast. Thank you all for attending. The recording will be available at aiha.webvent.tv. We will send all registrants an email tomorrow with this link, and please visit our event calendar to sign up for future webcasts.